crawling around, searching for higher ground. Can't see in front of me, my enemies. I've tried every possibility, ability to know if I can bleed. If that's what you wanted, you won't get it tonight. 'Cause I can fly, I can fly, I can fly, I can fly. I'm crawling around, searching for higher ground. Can't see in front of me, my enemies. I've tried every possibility, ability to know if I can bleed. If that's what you wanted, you won't get it tonight. 'Cause I can fly, I can fly, I can fly, I can fly.
All right, we're getting started. Welcome to Structural Congress. Today's session is about diverse and illustrative bridge case studies. Just before we start, please, if you need PDHs, please scan your ID at the door, and then don't forget to use the app to get to do a quick survey about the session. This is a live stream session, and today's speakers, I'm going to present them all at one time so that we don't take time from them. There will be 4 presentations. The first one regarding I-75 over SR-50, Twin Bridges by Henri Simpson from Hardesty, Principal Associate from Hardesty and Hanover. Second will be the North Washington Street Bridge by Piyush Rohela and project engineer, and Edward Bowman, senior project manager at Alfred Bench and Company. The third presentation, Why Are We Building a Bridge Here? The Replacement of the Boner Bridge by Dominic Coletti, Principal Professional Associate from HDR. And then the last presentation is about the I-75 segment ramp H4 Twin Top Girder Bridge by Leo Rodriguez. I'm the moderator. My name is Hossam Abdu. I am with Alpha Bench and Company as well. With that, Henri.
Good afternoon. I'm Henri Stinson with Hartsey in Hanover. I was EOR for the I-75 over State Road 50 bridge that turned out to be the longest bridge for a single span in Florida. So just to keep the story going, we're going to have a little agenda with setting up the project a little bit, and then we'll discuss how we had solutions for all the challenges. And you can see the site there, gives you a little bit of idea what we are talking about right away. So the project's about an hour and a half west of here on the I-75 corridor. If you take State Road 50, you can get there almost directly. It's owned by FDOT District 7, and the scope was part of a bigger project that was about 6 miles long in a design-build format with about $95 million construction costs. Hartsey and Hanover were the interchange designers as well as the maintenance of traffic or temporary traffic control engineers for the whole corridor. Just to acknowledge other people on the job, the one-man group was the prime engineer and the Middlesex Corporation was the contractor. So just to kind of establish the needs for the project, the interchange itself was substandard. I think the bottom line really says everything. With the projections of traffic, there will be a level of service of F at that particular intersection. It was one of the traditional urban interchanges you see around. The existing bridge itself had some issues. The clearance, probably the major one geometrically, but really this is more of a obsolescence, a need to upgrade the interchange entirely. There is a history of trucks hitting the bridge because of the low clearance, but the bridge itself had some more service life in it, even though it was from the 60s. Okay, so the new interchange layout. After a long study process and also ATCs and design build, it was settled on a single point urban interchange to meet the future level of service. And you can see the configuration there with the blue and the bridges are in the orange. The I-75 corridor will have 6 lanes in total for this build with provisions for future widening to 8 and 10 lanes. And the State Road 50 roadway beneath the bridges were widening, have 3 through lanes, large median, shoulders. And if you start looking at those numbers, you can see them kind of adding up to why the bridge starts to get so long. Also, if you just think about some of the sight lines from those ramps all the way out there that you need to be able to see through, and that spuies in general, they need to have no piers allowed in that whole blue area below the bridge to allow for those turning movements. So you can see why this bridge is getting long. So now to try to go through our design solutions, we're going to talk about the bridge itself and why we made these choices, and then how do we implement them with the maintenance of traffic and the constructability concerns moving through the project. So the structural configuration. So the record number is 298.5 twin simple span bridges. I think we missed the national record by a few inches, but inches matter sometimes. The bridge width is nothing big about it. It's 59 foot wide. That 1 inch is for a ½ inch that floats around in the parapet widths. We designed it for 6 lanes, but for provisions for future 8 lanes, and also some considerations for the future 10. Vertical clearance was set for the signs and whatnot, and also had to include some live load deflection, which is not normal, and we'll discuss that a little bit more moving forward. Pile supported end bends and retaining walls. So nothing here except the length is really non-conventional. And this kind of, I want to stress this is kind of a conventional plus bridge, and I'll try to point out where the pluses are and why they had to be a little bit more consideration for that. So that elevation there might not impress you too much, but it's a very long bridge. So here's a typical section. The 6 lane is what we're designing for right now, built right now, and we had to think through the 8 lane. The 10 lane was a little bit way in the future, but our provisions can handle the 8 lane configuration. You can see typical sections, there's nothing abnormal about it, so it's just the depth of the beams that might jump out at you. In this case, we have steel plate girders with traditional concrete decks on there. So with that span length, bearing to bearing length that you see there, we kind of got a little bit into la-la land because the AASHTO distribution factors are limited at 240 feet. So in order for us to responsibly proportion the live loads to those girders, we needed to do some calibration of our own. And it's something that we've done a lot. Leo will talk about it more later too, is that using those MDX design type tools, but we calibrate it with CSI model that allows us to kind of have an independent check and make sure that we're not doing anything that we shouldn't be able to do. And also this live load deflection. Now, in addition to capturing the live load distribution, we wanted to have a check of the natural frequency of the bridge, being that it's that long. We want to make sure we won't do anything that jeopardizes it from a resonance perspective. So the girders are 10-foot deep, 10-foot 6 deep web. We use grade 50 in the web, grade 70 in the flanges. It's a 1-inch thick web, and the flanges maxed out about 3 inches. Traditional deck, the dead load camber is a number that jumps out at me as well. It's a 25-inch camber, a couple of feet of camber, which is, striking. The live load deflection is about 4 inches, and that's why we had to include it in the actual clearance numbers. And neoprene bearing pads and pour joint system, 2 very simple, durable parts of the FDOT kit. Now, the first bullet there, this design was really controlled by constructability. The 1.4 dead load AASHTO case was really well designed, and the proportional limits of these girders, we could have probably done a lot of this design on the back of an envelope and got to where we wanted to be with the steel, but it's such a simple system. But even though it's simple, there are a lot of things to think through. So this is it in the fabrication yard. You can see the girder, maybe the ladder might give you some scale of the depth. And then you can see that string line there next to the flange on its side that shows you that 25-inch camber that we had to have to get to where we need to be with all the deadlifts on there. And then using the international measure of length for anything large, the football field, we can see that in that lay-down yard with that panoramic view, it's almost the same length. So it was pretty impressive to see laying on its side like that. Kind of a little bit of illusion when you look at it, like it shouldn't work, but works. So some other details, the owner chose to use weathering steel since we're not near the water. That's where that brown patina is. And with that comes some little details to move water away from certain ponding in some areas on the bridge. You can see the overhang brackets kind of hitting mid-web on the left there, and that's not always desirable, but we had a nice big 1-inch thick web that can handle those loads coming from the wet concrete pours on there. Also, you can see stay-in-place forms, just some of the splices in there. Foundations, the foundation itself is just 2 end bends, a single span. We had staggered 24-inch pre-stressed piles, founded on pretty good stuff there, so they didn't have to be too long. The stagger allowed us to not have to worry too much about moment, or overturning on there. The substructure itself, traditional class 4 concrete 5,500 PSI, and pretty deep back wall because we have to go all the way up to the top of the bridge from that 10-foot girders. One thing to note, this is one of the plus issues, is that we actually needed to pour the back wall after we had put all the load on that dead loads. The rotation at the end of the girders was so much that it actually impacted the back walls, and we had to straighten those up before we could pour those back walls. I'll talk a little bit more about that moving in. So walls, 30-foot-ish walls that, keep the whole structure in the right-of-way. Didn't have enough right-of-way to have slopes. These are proprietary, typical MSC walls you see all around Florida, where you could use steel straps in there since we're not near the water. And we needed to have some space there per RFP, the design build. One of the techniques that we used behind the back wall was to actually put a wire wall that was going to be buried behind the back wall permanently to relieve the lateral loads on the back wall since the back wall was so high, and also allowed us to have an embankment that was fully built and compacted before we even put the girders in place. So it gave the contractor some more flexibility in staging his work. And also, like I said, allowed us to build that back wall after the deck was poured onto the bridge. So how do we implement our design? And again, this was a design build contract type, so there's a lot of interaction with the contract on how we go about doing this. I won't talk about the drainage requirements too much, but it did control the width of the temporary structure you'll see in a second, because this is an interstate facility, and we need to make sure that hydroplaning and those things are taken care of when we narrow bridges. So we needed to make sure we had temporary drainage considerations. The steel girder erection strategies was something we worked through a lot with the contract and the erector. Temporary critical walls to be able to make cuts and give us space to build things. And I mentioned those camber and deflection implications a little bit with the back wall, and we'll talk a little bit more about that as well. Now, MOT does drive these projects a lot, keeping that traffic flow on I-75. It can never stop. So in a way, that's kind of one of the big design constraints on us is how do we keep traffic moving in these high-speed facilities and build these systems. So construction sequence. So we built the northbound. The contractor built the northbound system first, but in order to do that, we needed to be able to move traffic off of the northbound existing onto the southbound. So to do that, we had to widen the southbound bridge to allow 2 lanes of traffic either direction. So there is a temporary widening of that bridge as part of this contract. Once we widened that bridge, moved traffic over, we were able to make some cuts to make space for this much longer bridge into that position. So just to give you a little bit of perspective of the size, the existing bridge was 174 feet long. It was actually 4 spans. So we had to get much more space cleared out for us right adjacent to that existing bridge, since we were putting everything back on the same alignment to save fill and embankment for the project. And so there's a lot of wall work here. So once we've got that southbound traffic onto the southbound bridge, we can build the new bridge, move traffic back over, and then do the same to the southbound bridge. So that's a good picture looking north. You can see the northbound bridge being constructed. The traffic's on the southbound bridge. So the widening was larger than the existing bridge was. And again, that was because of the drainage requirements, needing to give enough of a shoulder so you could have that spread. Superstructure and substructure were just, basically what was there, the cheapest kit you could get to put out there. But there's a lot of wall systems. And what's interesting about the walls is that we use these temporary walls on one face with soldier pile lagging, and then we build next to it with wire wall, and then that wall comes out. So it's almost like a 2-sided wall setup. I'm not sure you can see that here, but that's the approach. So this is your temporary soldier pile and lagging walls, and against that, closer to where the picture's taken, you'll be building up the new embankment with a wire wall, because you're going to have to remove that lagging once we've moved traffic over. So with the bridge erection itself, one of the innovative things that we came up with during this project was to reuse the existing piers of the existing bridge as temporary shoring. Because we're limited to about 130 foot of length of girder to transport, we need to have a couple of splices to make up 300 feet. And we designed our girders strategically with the existing piers in mind, doing things like putting a stiffener bearing right over the temporary bearing area, and making sure our splices had enough space to be put together outside of the footprint of these piers. So this saved some time in putting temporary shoring in place, and gave us a pier that we knew was going to work. So in this picture, you can see the existing southbound bridge to the left with the widening, and on the right, this is the northbound with one additional pile to use as that temporary setup. And there you have the bridges. Looks like all 3 pieces of the bridge is in place with the temporary shoring of the existing pier. And you can see the back wall in the distance on the right picture is not in place yet, just a cheek wall. So you can see daylight back there. And on the left picture, again, another image of that space we created with that soldier pile lagging wall. So that was a long night out there, but it was very nice to see it get in place. So here's another one of these plus issues. So, we were able to use the most durable bearing setup there is, a nice neoprene elastomer. But with the amount of camber and rotation, once you start putting load on that with the deck pour, you start to get a lot of horizontal movement with these bearings. On a shorter bridge, usually those movements are within what's tolerable, and you don't need to worry about the stability of the bearing. But in this case, we needed to be able to get that to get that deck pour, flatten everything out to where we want to be, and then jack to reset those bearings. And we checked all the bearings to make sure they hadn't exceeded their allowable deflection, and if any did, we replaced those, but we reused almost all of them. So you can see some of the movements here from the dead load itself are not trivial movements, and it's something you need to consider dealing with a very long span like this, is how are those end lateral displacements affecting your bearing initial set and back wall. So in closing, this was a great project for us, very challenging, that, in the design build environment, getting to work through these issues with the contractor and vet our ideas directly with the person who's going to be implementing it was great. It is another one of those things that we've seen, that the new demand on right-of-way and traffic service, we're pushing us into these different interchange configurations, which means that we have to come up with different structural solutions for them. And again, this conventional plus concept of, yes, in cross-section and maybe elements, it's a normal conventional project, but there are some things you need to put a magnifying glass on when that plus comes into conventional. So thank you very much. That's
Thank you, Henry. Good afternoon, everyone. I'm Ed Bauman with Alfred Banish and Company. I'll be talking about the North Washington Street Bridge replacement up in Boston. Piyush Raella will come up midway through our presentation and talk about the structure itself. I'm going to focus on the development of the roadway that the bridge carries. As you can see in the center of the image is the bridge crossing the Charles River, just downstream of the Bunker Hill Monument Bridge, Bunker Hill Monument Bridge, and there is the TD Bank Garden, home of the Boston Bruins and the Celtics. Ooh, I'm sorry. Green. The City of Boston is the owner of the bridge, a major proponent of the project. Mass DOT Highway Division is the overseeing the design and construction of the structure. FHWA is our lead federal agency. All three are participating in the construction costs of the structure. Alfred Banish and Company, the lead structural and civil highway engineers, and Rosales and Partners are the bridge and highway architects. Here you see the existing bridge. It's actually beyond the Charles River, and it's actually over the Boston Inner Harbor. You see the center portion of the bridge. It was a swing span. It was 100 feet wide and 240 feet long. There are 10 approach spans, and the total crossing is about 1,100 feet. In the foreground, you see the Zachem Bridge and the Charles River Dam and the Gridley Lock system that leads you through the entrance to the Charles River to the harbor. To the left of the screen, you see the Charlestown area of Boston, which houses the USS Constitution and the Bunker Hill Memorial. And the right side of the screen is Boston's North End, known for its festivals and Italian cuisine. And the historic Freedom Trail crosses the structure on the east sidewalk. The bridge is located between two traffic signalized intersections in Boston. You can see from this aerial view that there are a lot of parks that have been developed along the Charles River, creating an exciting area and an up-and-coming area of Boston, and the value that the replacement of this project will help add to the area. The function of the existing bridge carries 42,000 vehicles per day. It also carries 4 major MBTA bus routes, and as well as healthcare shuttles in the area. A recent study found out that identified this corridor as a hot spot for major delays for bus travelers. And while buses make up 3% of the vehicles, they could carry up to 34% of the users of the bridge. There's also cyclists and pedestrians crossing the bridge. That picture at the top shows how in the center span, the swing span, the trusses break up the roadway into 3 separate roadways, each carrying 2 lanes of traffic. The center bay was closed about 15 years ago due to deterioration, so now there's only 2 lanes in each direction crossing the bridge. If you are on a bicycle, you have to decide whether to stay in that narrow roadway or to mix in with the pedestrians. And that section of the bridge also has open grid decking, which is makes a lot of noise under traffic and is unsettling to a lot of users. There's also numerous utilities crossing the bridge. Since the swing span no longer swings for the past 50 to 60 years, there's many utilities crossing the bridge, including electrical transmission and distribution lines, a gas main, water main, communications, and traffic signal interconnects. And obviously the bridge allows for water to flow underneath it as well as boat traffic. So the bridge has been in service for about 120 years. The marine environment is extremely corrosive, and the city has been spending about $2 million a year for the past 15 years maintaining this structure to keep it open to traffic. A lot of steel repairs, every inspection cycle becomes new repairs. And eventually was decided to replace the structure completely. Since this structure is considered eligible to be listed as a historic place, that for a replacement triggers a Section 106 review of the National Historic Preservation Act. This review is a collaborative effort between FHWA, the State Historic Preservation Officer, Mass DOT, City of Boston, local historic commissions, and the Native American councils. And the result of this process is a memorandum of agreement listing design requirements to allow the replacement of this potentially historic structure. And these are the requirements for this project: is to create a gateway bridge, provide a context-sensitive design, and distinguish the structure as a place in itself. And they recommended architectural lighting, architectural structures, overlooks, separated bike lane. And they built into this memo that we need to provide elements to encourage use by people of all ages and interests. This memorandum of agreement is consistent with Mass DOT's healthy transportation policy and statewide Complete Streets program. Complete Street is defined as one that provides safe and accessible options for all modes of transportation: walking, biking, transit, and vehicles, and for people of all ages and abilities. This Complete Street design is also another collaborative effort with Mass DOT, City of Boston, MBTA, which is our transit authority, DCR for the parks in the area, and all the advocacy groups for pedestrians, cyclists, and transit users. The result of this effort was 57.5. That's how close we got to negotiating every foot of width of this space. We resulted in a 57.5-foot wide roadway carrying 2 lanes of vehicular traffic in each direction and 1 designated bus rapid transit lane in the southbound direction to help reduce the delays for those users on the buses. We have our crash-tested barriers along the face of each roadway, which was used to create longitudinal planters that separate the bikes and peds from the traffic noise and hazards. These planters provide areas for street lighting as well as areas for that architectural trellis that you see on the screen. That architectural trellis was used to mark the crossing. For the last 120 years, we had the 33-foot high truss in the area, and we knew that would be missed, so we provided the similar scale trellis structure to mark the crossing for both the roadway and the boats down below. On the other side of the planters, we decided on having a 7-foot wide bike lane in each direction following the traffic direction. The 7-foot wide allows for faster cyclists to pass slower cyclists. And there is a 3-inch high vertical curb that provides vertical separation between the bikes and the 10.5-foot wide sidewalk on each side of the bridge. And that pedestrian railing is an aluminum stainless steel illuminated railing system. And then the sidewalks widen up to 19 feet to create those overlooks, which will have tree planters and benches to allow a place to rest across the bridge, get some shade halfway across the bridge, to cover that, designing for someone who is 8 and 80. So if you can't need a place to rest halfway across the bridge, we have one. And there'll also be landmark plaques describing the views from the bridge. There's the Bunker Hill Memorial on that view there. And this is, since the bridge to be designed in the context of the area could not compete with the Zakim Bridge. The Zakim Bridge is such a massive structure. It couldn't contrast or compete with that. So this bridge was viewed as a viewing platform for all the viewings of the area. So the unique structure had to come from the substructure on the bridge. And if you've seen the Zakim Bridge, it has 300-foot high inverted Y pylons. And you'll notice the architect built in an inverse of that with V-piers for our structure. This is an elevation of the bridge showing those V-piers, showing how they reflect in the water, and you can see the Zakim Bridge in the background. I'll go back to the previous slide, hopefully, and you can see the roadway elements that we described earlier, the build-outs, the trees, the benches, the separated bike lanes, the bus lane, and the vehicle lanes. And both the architectural trellis and the V-piers will have accent lighting, so they can light up the area and match the lighting on the Zakim Bridge, which changes colors due to the holidays or sporting events. And now I'd like to invite Piyush to come up and talk about the bridge structure.
Thank you, Ed, for these, providing us a context to this bridge's design with these mesmerizing renderings, very colorful. Now we move on to the more black and white portion of the bridge design, or if you attended the plenary session today morning, the part of the presentation where we say structural engineering inside. The choice of the cross-section of the bridge was determined by two factors: the use of conventional methods of construction and a high score on constructability. The geometry of the cross-section, however, and the layout of a lot of cross-section elements that you see here were determined by two high-pressure fluid-filled transmission lines that were going under the west sidewalk. These could not only be moved anytime during the construction of the bridge, but also had to be supported every 10 feet throughout the duration of the entire project. The steel box girders were chosen for their high torsional rigidity and for a shallower profile compared to the I girders. They were also 6.5 feet deep to allow convenient inspection in the future. Like Ed mentioned before, the existing bridge consists of 10 approach spans and a central swing span, which has been in the fixed position since 1961. So we were limited to the choice of arrangement of the new spans, mainly by locating the piers steering clear of the existing bridge foundations, of which there were many. Also, and also by the desire, or rather for structural engineers, requirement to maintain the navigation channel to be in open position throughout the project. The city of Boston is known for a lot of things. However, good soil profile is not one of them. Under 30 feet of water lies 30 feet of silt and clay, below which we find some quality glacial till. The 30 to 80 feet deep drill shafts were rock-socketed, or would be rock-socketed, 10 to 27 feet into the rock strata to get the desired geotechnical resistance. Here you can see several views of a typical V-pier. So underneath each girder is one V, which is supported on one column. And 4 Vs constitute a one V-pier. They are supported on a 5-foot thick drill shaft cap, and underneath are 8 6-foot diameter drill shafts. The way the tie beam ties the arms of the V-pier is shown on the left. In the stage 1, a precast tie beam is just placed on a shelf that's created on top of the arms. The post-tensioning threaded rods are put in, and it's post-tensioned to 300 kips. What it does is it brings the arms closer together and helps later on when the dead load is added. But after the first stage of post-tensioning, the joint between the arms and the tie beam is grouted, or the closure pour is completed, and additional 2,000 kips of post-tensioning is applied. Next, the ducts are grouted, and the steel is erected, and then comes the deck pour. The cofferdams were designed to minimize the time spent in water and to minimize the overall footprint of the foundation. On the top right, you see the proposed platform that can be used to create and support the V-pier arms. The box girders also allow 2 major construction stages where the bridge would be acting, the half of the bridge longitudinally would be acting as an independent structure itself. And on the left of both these views is the temporary utility bridge would be in place throughout the construction of the new bridge. Midas Civil was used to create 2 full bridge models, one with the substructure and one without the substructure. The model without the substructure was used to design this superstructure. A separate model in MDX was independently created. The similarities and differences of the results was analyzed until a good confidence level was reached. The model with the substructure was used to determine the forces for substructure design because that accounted for rotations of the pier as frames themselves. And after the forces were determined, the substructure was independently analyzed and designed using Midas Civil and STAD. Lucis was the software of choice for seismic analysis. This shows screenshots of the V-pier, one of the V-piers and the tie beam in the 3 stages as described earlier. And the number of times the engineers in office raised their hands up and out and swayed from left to right was so many that it became the unofficial greeting in our office. Here we can see the rebar arrangement on the left at the top of the arm. You can see it's really congested. It also shows a 12-inch long closure pour with the tie beam, and below that is a shelf where the tie beam is initially placed before it's post-tensioned and grouted. On the top left, we can see the cross-section of the tie beam again. It shows currently 8 post-tensioning threaded rods, which have now been updated to 10 to introduce more post-tensioning up front. And on the lower left, you can see the typical cross-section of the V-pier arm. What's interesting is that the offset in that the reinforcement in the arms is offset laterally so that it can cross each other clear at the base of the V as seen on the right. This shows the typical cross-section in somewhat greater detail. Notice the shaded area of the deck beneath the sidewalk. That's where the lightweight concrete would be used. In the main span, that's span 7, and its adjacent spans 6 and 8. That would be to reduce the imbalance on the V-piers adjacent to the main span. It also shows a few more utilities being carried by the bridge. This is a similar cross-section, except it's at the center of the bridge where it is at the widest. Notice 19 feet, 1 inch wide sidewalks, deeper floor beams to carry these long cantilevers, and extra stringer to support the widened sidewalks. This shows a typical connection of the floor beam to the exterior box girder. It's a typical end plate moment connection with the tie plate on top, and the bottom flange of the floor beam inside where it connects to the web of the girder has a CJP weld which meets the AASHTO Category C fatigue design requirements. Another similar details except at the widest portion of the bridge with a really long cantilever and an additional stringer to support the widened sidewalk. The barrier consists of a T401 rail for the vehicular side of the bridge. The wall on the right is for the bike lane, and it houses electrical conduits. The longitudinal planter that runs for the full length of the bridge is shown in the middle with a complete irrigation system. And the barrier also provides support for lighting and architectural trellis. The pedestrian rail on the right-hand side is an illuminated infill cable type rail, which would be mock erected and load tested before installation. Here we can see the contractor's proposed sequence of construction, where the contractor is proposing a full-length temporary vehicular bridge on the west side of the existing bridge, and there is a temporary utility bridge just abutting the west side of the existing bridge too. In the proposed construction stages, in stage 1, the temporary bridges would be constructed while the west sidewalk is demolished. In stage 2, the traffic is going to be moved on the temporary bridge while the existing bridge is demolished, and the entire east half of the bridge is constructed, but only 70% of the west half of the bridge would be constructed. In stage 3, the traffic would then be moved to the newly constructed east half of the bridge, and the temporary vehicular bridge would be demolished. Following that, in the last stage, the west sidewalk would be constructed, the utilities would be relocated back to the bridge, and this would complete the new North Washington Street Bridge. Currently, the project is in stage 1, where the construction of the new temporary bridges is underway, and we hope that by the spring of 2023, the renderings that we showed today would come to life. Thank you. This concludes our presentation, and over to Dominic for the next.
Good afternoon. My name is Dominic Coletti. I'm with HDR Engineering, and HDR was fortunate enough to be the lead designer on a design-build team led by PCL Civil Constructors for an NCDOT project to replace the Herbert C. Bonner Bridge over Oregon Inlet on the North Carolina Outer Banks. The title of this presentation is Why Are We Building a Bridge Here? You'll see why I chose that title in just a minute. As we go through the outline here, we're going to ask that question first. When you think about it, this is really kind of a crazy place for a bridge project. We're basically building a bridge between two sandbars right on the Atlantic Ocean. We're going to see how some conditions, constraints, and criteria affected some themes that we followed as we entered the design of the bridge. Then we'll show you how that design played out, the final product, and show you some construction photographs, and wrap things up with a quick summary. So let's begin by asking that question: why in the world are we building a bridge here? There's three main reasons. The first is the mantra of the realtor: location, location, location. The second is the mantle of history, a sense of tradition at this site. And third is the answer you get when you ask somebody why they climb a mountain: just because we can. So let's begin with that first reason, the location of the project. If you haven't been to the North Carolina Outer Banks, it's a 200-mile-long string of barrier islands on North Carolina's Atlantic coast. It's a beautiful area. It has beautiful beaches, pristine natural wildlife environment, and great sport fishing. It's been a destination for a lot of people for a long time. There's a lot of history at this site. The Oregon Inlet itself originally opened back in 1846 when a storm blew a breach in the Outer Banks Islands. People have been coming to the Outer Banks for a long time since that time. For a long time, the only way they could get around through the Outer Banks Islands was by ferry service. And North Carolina Department of Transportation helped to aid that a little bit when they completed the construction of the Bonner Bridge in November of 1963. About 2 years later, they were out there again starting to do maintenance and repairs. This is a really harsh environment to have a bridge. They were seeing a lot of scour, a lot of severe deterioration. This bridge became a constant maintenance nightmare for the next 50 years. To add insult to injury, in October of 1990, a dredge broke loose during a storm, struck the bridge, and took down 6 spans, cutting off access for several months. It was around that time that NCDOT got serious about coming up with a permanent replacement for the Bonner Bridge and began a planning project that extended for over 2 decades. It wasn't until 2011 that they were able to award a design-build contract to PCL Civil Constructors to replace the bridge. Finally, the last reason why we'd want to build a bridge here is just because we can, because we're engineers and we love a challenge. There are plenty of challenges at this site. Lots of constraints. We were dealing with very weak soils, very deep foundations. Those foundations are subject to very severe scour, as you'll see through the course of this presentation. And there were, of course, a lot of stakeholders. A lot of people wanted to have a say in how we designed and built this bridge. We also were facing a lot of goals, sometimes competing. NCDOT, for their part, wanted to have a very durable structure, one that would be low maintenance and have a long service life. PCL wanted a bridge that was very constructible, a structure that they could build easily in this very harsh marine environment. And everybody wanted an economical bridge, one that could be built for a reasonable cost. Now, I mentioned scour as one of the primary drivers in this project, and I want to help to illustrate why that's so important here, and to show you the nature of the project site. Oregon Inlet is one of the most dangerous inlets on the Atlantic coast. It's a highly dynamic inlet with very regularly changing bathymetry. The best way to show that is through a series of aerial photos taken over time. This is beginning back in 1996. In the upper left-hand portion of the photo, you see the southern end of Body Island. In the lower right, you see the northern end of Hatteras Island, and that sharp edge is a rock revetment called the terminal groin that helps prevent further migration of the inlet to the south. Running from upper left to lower right is the existing Bonner Bridge, and we've marked the existing bridge's navigation span to give you a point of reference. Now, as we walk through time, you can see that the inlet changes shape and size dramatically. Body Island moves further south, further north. The inlet closes up, it opens up again. This is one of my favorite photos. It was taken in the spring of 2011. We were right in the middle of the pre-bid engineering work, the pursuit phase of the design-build project. You can see that the southern end of Body Island has migrated so far south that it's actually blocking the existing bridge navigation span. And if you look closely, you can see a Corps of Engineers dredge working one span to the south as furiously as it can to keep any kind of navigation way open. Not to fear, Mother Nature to the rescue. Along came Hurricane Irene, blew the inlet wide open again a few months later. Really a dynamic place, lots of challenges here. We're going to see how some of these challenges affected how we approached the design of the bridge next. And I'd mentioned lots of different conditions, constraints, and criteria that we were working with. We tried to always keep in mind that we were building a very long bridge, 2.8 miles long. We wanted to see a lot of repetition so that we could get some economy of scale in the design. We always had to remember that we were working in a very remote location. Access for delivering construction material, equipment, and so forth is really challenging at this site. We were building in 3 different construction type sites. We had overland construction, we had construction over shallow water seagrass beds, a submerged aquatic vegetation area, and then we had deep water construction out in the inlet. Out in the inlet itself, the design had to accommodate a 2,400-foot wide navigation zone. Anywhere within that 2,400 feet, the bridge had to provide a minimum 70-foot vertical and 200-foot horizontal navigation clearance. We had that challenging subsurface profile with the loose sands extending very deep. We had that scour to worry about with 5 distinct scour regions, and we had the design for a lot of horizontal forces, vessel collision, currents that are generating a lot of water and wave forces, and a faster than normal design wind speed of 105 miles an hour, and that's under the old AASHTO fastest mile of wind criteria. NCDOT really wanted to have a very durable bridge here, and they made sure that it was clearly communicated in the RFP. They began with a basic criteria of a 100-year service life, and then they went down into some more prescriptive requirements and prohibitions. They prohibited the use of structural steel anywhere on the bridge, no structural steel girders or piles. They specified that any cast-in-place concrete had to be reinforced with solid stainless steel reinforcing. You can see some of that in the lower right photo there. Keep in mind, stainless steel reinforcing costs 3 to 4 times as much as regular black reinforcing, so this was a pretty onerous requirement. They also specified that any post-tensioning in the substructure that was within the splash zone up to 12 feet above mean high water had to be stainless steel post-tensioning. But they did give us a break in a few places. They allowed that precast concrete could be reinforced with regular carbon steel, black reinforcing. The concrete itself had a very prescriptive mixed design with high percentages of fly ash or ground granulated blast furnace slag, silica fume, and calcium nitride corrosion inhibitor. This made for a very robust, very durable concrete mixed design, one that's very resistant to corrosion, but it's also a mixed design that's very difficult to work with in the field. Early on in the project, we keyed in on the need to extensively use precast concrete. This allowed us to minimize the quantity of that very expensive stainless steel reinforcing, It also allowed us to achieve much higher quality fabrication. All these precast elements were fabricated off-site under controlled conditions rather than in the harsh salt spray environment of Oregon Inlet. This also allowed us to achieve a lot more reliability and a lot more improved durability. That high quality fabrication led to a much more durable, long-lasting structure. We got much more reliable delivery since we were delivering precast elements rather than worrying about whether a traffic jam or some other incident would delay delivery of concrete trucks. Overall, it also led to a reduction in the field work, which made things go much more quickly, much safer, and much higher quality construction for PCL working in that harsh marine environment. And as a bonus, we were able to greatly reduce environmental impacts by reducing the chances for concrete spills and so forth. To that end, we precast everything we could on the project, not just girders and piles, but also bent caps and columns. One of the touchstones throughout the design of the project was this longitudinal profile. It shows a lot of information and really helps you understand the nature of the project. It shows a subsurface profile. The yellow there is that loose, low blow count sand. It extends as deep as 120 feet in some places. And it overlays that pink layer of high blow count dense sand, which is very good for foundations. You can also see the 5 different scour zones, and the scour profiles are shown there. The red is the 100-year scour, which extends as deep as 84 feet below mean high water out in Scour Region 3. You can also see the profile of the bridge where it needed to be taller with longer spans to accommodate that navigation clearance. Remember, we mentioned we wanted to have a design with a lot of repetitive elements to achieve economy of scale. We tried to limit ourselves to very simple elements, and just a few of them. We had 2 main foundation types, a 54-inch cylinder pile and a 36-inch square pile. 3 main substructure types, a very economical all precast pile bent system, a 2-column bent system, and then precast post-tensioned hollow single-column bent. We had 2 main superstructure types rather. Most of the bridge uses 96-inch deep precast pre-stressed Florida I-beams. And then when we're up in that high-level, long-span navigation zone structure, we had a variable depth, precast post-tensioned concrete box girder. Now we took those few elements and we started to assemble them into different combinations so that we could tailor the design of the bridge to the unique needs of each one of those 5 regions that we had identified based on the span length requirements, the structure height, the scour depth, the vessel collision forces, and so on. And you can see how we pieced together the design using those few simple elements to come up with a design that used a lot of repetition, very simple elements, but was tailored to the unique needs of each one of those design regions. So we're going to see next how those themes played out in terms of the final design and construction of the bridge. And we're going to begin in the north and south approach spans. These are low-level structures starting from the ends of the bridge and coming up towards that high-level navigation span. The north approach span in particular is a pretty significant structure. It extends about 1.5 miles. It's a very simple structure. It has a cast-in-place concrete deck with precast 96-inch deep Florida I-beams, and that's resting on that highly economical all-precast pile bend system with a precast bend cap and 3 or 4 of those 54-inch cylinder piles, all oriented vertically. Now, for any kind of structure like this that's subject to very high lateral forces, vessel collision forces, wave forces, wind loads, and so forth, and deep scour, where you've got a deep depth down to the point of fixity of the structure, you need to take a long, hard look at doing a very refined soil structure interaction analysis to really help you optimize the design of the structure. We did that throughout the project here, and to that end, each and every one of the bents on the project has multiple FB multi-pier models. We modeled different scour depths, different loading conditions, and so forth. PCL, for their part, made some innovative approaches when they approached the construction of this bridge as well. You can see a photo here of the north approach span construction through that submerged aquatic vegetation area. Through this area, they were using work trestle construction, which is fairly conventional, but the innovative twist is that they started to leapfrog their work trestle as they progressed the work. Construction began at the north end of the bridge, work bridge and the permanent structure together, and when they had extended down to about 1,000 feet along, they started to pick up spans from the work trestle from the tail end of the construction, migrate them over to the leading edge of construction. This allowed them to limit the amount of work trestle material they had to invest in the project, but more importantly, it was really a big hit with the environmental agencies because it minimized the temporary environmental impacts caused by that work trestle. Now, there was a price to pay. Once you cut off your access to land from that work trestle, you had to have all material delivery come from the existing bridge. You also were limited in the work area that you were working on from that work trestle. We're working in a very narrow corridor between the existing and new bridge, and you can see that the cranes are fairly big to pick up the large elements, the large precast elements we have here, and they take up nearly the full width of that workspace. As we move along from the north and south approach spans and start transitioning up to the high-level structure, we go through two regions that we call the north and south transition spans. Here we have that same economical structure, superstructure with a cast-in-place deck, the precast floor to I-beams. This time it's sitting on a two-column bent with a precast bent cap and precast post-tensioned solid columns. Those columns are resting on a cast-in-place footing with multiple 36-inch battered square piles. We started using this foundation system as we got out into the deeper water with deeper scour and higher vessel collision forces. Again, there's extensive use of soil structure interaction analysis here. We really needed to do this to dial in the design of each one of these foundations. It's a couple of photos showing construction of the south transition spans. All of this work was done from barges out in the deeper water of Oregon Inlet. There's some fairly long spans here in the south transition span region. These Florida I-beam girders that we had placed spanned up to 182 feet. These are the longest simple span precast girders in North Carolina. Finally, we got to the high-level navigation spans. This is the part that everybody's interested in. This is the sexy part of the project. Here we have a precast post-tension segmental concrete box girder superstructure, and it's supported on single-column bents with a precast pier cap, precast post-tensioned hollow box columns, and then that cast-in-place footing with multiple battered 36-inch square piles. Now here, that soil structure interaction analysis was taken to one more higher level. This navigation unit is a single continuous 3,550-foot long precast post-tension concrete box girder structure. It's subject to very high wind loads because it's a fairly long span and deep structure. It's got high vessel collision forces, and perhaps most importantly, it has very significant creep, shrinkage, and thermal deformations. It's 3,500 plus feet long, so the movements are very significant. The designers had to go through multiple iterations just to determine the number of fixed piers to include in the structure, balancing the need to have enough fixed piers to carry force-driven longitudinal loading effects like wind loads and braking loads, while allowing enough freedom, enough free bearings to accommodate those big deformations. The designers went through 14 complete design iterations before they settled on the final design here. It's a few photos of construction. Some of this construction is fairly dramatic. You can see that the 36-inch battered square piles are in place to be driven into the ground, jetted and driven into the ground. These piles were up to 140 feet long. You can see in the background the balanced cantilever construction of the 350-foot long spans. And I really want you to notice the weather conditions here. A lot of people think that when you're working on the Outer Banks, it's all sunshine and sunscreen, and you're sitting there on the beach with drinks with little umbrellas in them. It's really not like that. A lot of the year, it's very cold, windy, and rainy at the Outer Banks. It's a really nasty place to build a bridge. PCL exercised some innovation here as well, especially with the foundation construction. It's kind of neat to see how clever contractors can be when they're faced with a challenge. For each one of these foundations, they began by driving steel piles into the inlet, established a fairly conventional-looking steel template, but then they really got innovative and installed some oversized steel casings that they could easily vibrate partway into the inlet's ground. And they could do that easily, which allowed them to very carefully control the constructed geometry of those casings. Once those casings were in place, they could install the 36-inch square piles. They would trip them into those casings, jet them down to nearly their tip elevation, and then drive them the remaining 10 or 15 feet. That allowed them to maintain very good control of the constructed geometry of those piles, which was critical for the rest of the construction of those footings. They would build those footings next. They were up to 8 feet thick, a lot of mass concrete construction, and then they would start construction of the columns themselves. You can see in some of these photos the stainless steel post-tensioning and stainless steel reinforcing. They would have a cast-in-place solid base and then begin construction of the hollow precast box sections, match cast construction, as they would erect the columns. Then they would begin construction of the balanced cantilever segmental concrete box girder superstructures. The cantilevers extended 175 feet in each direction before they would reach out and come close to the cantilever from the next span, at which point they would cast a 4-foot closure pour. Really dramatic construction techniques not something that's commonly used in North Carolina. With that, we're going to wrap things up here. As I mentioned at the beginning, the basic question we wanted to answer was why in the world would we want to build a bridge here? It's kind of a crazy place to build a bridge. A lot of challenges here that affected how we approached the design of that bridge. And we showed you how those challenges framed the approach to the design and how we used a very few simple repetitive elements, but combined them in unique ways to tailor the design to the unique needs of each one of the regions of the bridge. We showed you the final product, how things played out in the design and the construction, and we're going to wrap things up with a few quick statistics. Our geotechnical engineers were sitting around board one day and started counting up how many piles they had designed. They had designed some 600 plus piles, 12 miles of the 36-inch square piles and 3.5 miles of the 54-inch cylinder piles. At that point, the bridge guys got jealous. They started adding everything up. We ended up with 25.8 miles of precast concrete, over 90,000 cubic yards of concrete, 2/3 of it precast. The project is coming along very nicely now. They had an opening ceremony just a few weeks ago, April 2nd. The bridge was open to traffic on February 25th. And PCL is basically down now to just a few punch list items on the new bridge, and they're working on demolition of most of the existing bridge. Most of it's going to be cut up into pieces, barged offshore, and used for artificial reef sites. And they'll leave about 1,000 feet at the southern end of the existing bridge as a pedestrian structure, fishing pier, and as a training structure to help anchor the southern end of Oregon Inlet to prevent further migration.
Good afternoon, everyone. I'm Leo Rodriguez from Hardesty in Hanover. And today I'm going to be presenting a project that I decided to title, Why Not Straddle It? Representing the I-75 Ramp H4 bridge and the integral straddle band cap. Today's agenda will include some introduction of the project, some of the project needs, a site overview, and some of our design solutions. The project is located in Miramar, Florida, and it is owned by FDOT District 4. So Ramp H4 is part of the Segment AB project, which is one of the largest and most complex segments of the I-75 express lanes being built in South Florida. And it consists of 3 miles of widening and reconstruction for a total construction bid of $234 million. Our role in this project was to be the lead designers for Ramp H4, H12, and H5. On this project, we partner with a one-man group incorporated. I wanted to give you a brief background and history of this stretch of I-75. It was originally conceptualized in 1961 to connect Tampa and the Miami metro area. It was finally built in 1986 as an 8-lane facility with 4 lanes each direction, and a very wide median reserved for a high-speed transit corridor. As part of the I-75 master plan, the FDOT in 2012 finalized a PD&E that was later reevaluated in 2013 that decided that this median could be used for express lanes and also save some space for a future transit corridor in the future. This was all done to improve on the link between between the Palmetto Expressway and I-595, and also help the commuters there bypass around Miami with a link to the Florida Keys. So why do we build it? Florida has been growing in the past few years, and that has translated into an increase in population and urbanization trends. For this stretch of I-75, the level of service is F, which for us as structural engineers means being stuck in traffic like 4 or 5 minutes more. They also wanted to improve the overall system linkage and connectivity, specifically the different modes or modal relationships of transportation. I-75 is a limited facility in the stretch, so there are no pedestrians, so the FDOT mostly focused on vehicular and transit traffic. They also wanted to improve on safety, and particularly on I-75 being such an important interstate when it comes to evacuation. Now, ramp H4 connects the southbound express lanes being built in the existing medium to a southbound exit on the west side of the heft. That means that this ramp needed to straddle at least 5 southbound general purpose lanes and provide 16.5 feet of minimum vertical clearance throughout its length, specifically at intermediate supports. Our client wanted durable structures and easy to maintain, and also limited our walls to be approximately 40 feet in height. There were other environmental considerations like maintenance of traffic and noise reduction during construction. So now that we discussed a little bit about the project requirements, I want to go over it with you, our design solutions, and I hope I can explain our design approach, the analysis, some of the decisions that we made, and the construction aspect of it. It may not be as interesting as the Avengers Endgame movie that came out last night, but I hope you guys can find any value of it. Please, no spoilers. So, ramp H4, because of the geometry and the clearances and the traffic movement that we needed to accommodate, we ended up having a 595-foot-long, 3-span continuous superstructure with very tight curves. The ramp had a 30-foot and 1-inch wide section that consisted of one 15-foot lane with 2 6-foot shoulders and variable super elevation. One of the ways that we were able to straddle the southbound express lanes was by providing a 115-foot-long straddle integral bend cap, along with other pile-supported bends, columns, and C-piers. At both bridge ends, we provided permanent retaining walls, in this case the FDOT Type 2B, to help us shorten the bridge length. On the structural design, as many of you know, piers and bends are very stiff structure. It is not the same for the integral straddle bend cap. When you combine this flexible support effect with the complex geometry that we have with the curvature and the super elevation transition, you get a very complex structure that is not easily designed by simple methods. This is why we developed finite element models with 3 main goals in mind. One, we wanted to understand the behavior of the structure and what the live load distribution was after we introduced this flexible support. 2, we wanted to make sure that the bridge natural frequency didn't show anything abnormal. And 3, we wanted to calibrate a design software with the results that we got from the finite element model. As many of you may know, finite element model softwares are great for analysis, but they're not as efficient when it comes to checking AASHTO design verifications. So on the right side, you can see the finite element model in its deformed shape due to dead load. And on the lower side image, you can see how closely both models that we calibrated were, which made us feel very comfortable in our design checks. We also provided additional analysis, specifically a multi-axial stress of von Mises criterion, particularly at the connection between the top girder and the straddle bend cap, because of the longitudinal and transverse bending effects that we were seeing at this location. We also did a similar analysis for the bearing stiffeners diaphragms because of the shear and moments that are a result from having a single bearing underneath each top girder. The analysis and design resulted in twin top girders, spaced at 16 foot on center. made out of grade 50 weathering steel. Weathering steel was selected because it was the material of choice for our client, and it's very low maintenance. We had 80 inches deep web with 20-inch wide top flanges and 72-inch bottom flanges. We decided not to vary the width of the flanges, but instead we varied the thickness of them when it was needed. And we strategically did that at field splices that coincided with counterflexure points. We ended up having a very conventional 8.5-inch concrete deck with half-inch sacrificial. For those of you that are not from Florida, Florida does not have an overlay asphalt on their bridges. We also had high-load multi-rotational disc bearings with a fixed bearing at Pier 4. That bearing was strategically located at the pier because it gave us some advantages that you'll see later on, and multi and unidirectional bearings elsewhere. One of the advantages of fixing the bearing at Pier 4 was that we were able to provide a simple pour joint on the shorter end of the bridge and a modular joint on the largest part of the bridge where the maximum thermal movement was being seen. Minimizing the amount of joints was something important for the client because it reduces the long-term maintenance. We also provided K-type frames and a Warren type top flange lateral bracing because they were the most efficient elements that could prevent distortion and improve the stability of the top girders during construction. For the integral bend cap, we detailed it as a box girder. As I mentioned before, it's 115 foot long. The whole length of the box girder is fracture critical. Very thick, our analysis indicated that we needed very thick webs and flanges as well. But we wanted to make sure that this integration with the top girder was done smoothly. This is why we detailed 4 feet stubs on each side that coincided with the flanges and the webs of the longitudinal top girders. We also sized this box girder to allow for the handling and transportation of it throughout the state. On the left side, you can see that before the splicing occurred, you can see those 4-foot stubs that are kind of mimic the same shape of the longitudinal top girders. And then on the right side, you can see the final longitudinal top girders already spliced into these box girders. We strategically made those flanking spans on the longitudinal top girders a maximum length of 40 feet to allow the erector to have a lighter element and easier elements to splice. Now, on the bridge foundation substructures types, we had a very diverse type of elements selected that maximize and were the best solution for each of their particular case. Starting on the south side, we have an end-pier wall that was founded on 24-inch pre-stressed piles. This pier wall not only supports ramp H4, but also supports H12 and serves as a transition between both ramps. We reinforced the backside of the wall with geogrid that help these pier wall handle the lateral forces from soil and maintain stability. Because of the aesthetics, our client required that we added some details for that transition between ramp H12 and ramp H4. So we make sure that the retaining wall that you see there on the left side, the left bottom side image, had a space for those retaining walls to tuck in. We also had independent piers that were also founded on 24-inch pre-stressed piles. These piers are critical for structural stability because they're the ones supporting the straddle bend cap. So they have a lot of conservatism in them. one of obviously the sign checks that we performed was the vehicular collision because of the proximity of the piers to the traffic. We also had C-shaped piers also founded on 24-inch pre-stressed piles. And mainly we chose this geometry because we needed to maintain that minimum vertical clearance on the eastmost lane and shoulders on the southbound general purpose lanes. Fortunately, the analysis showed that we didn't need any post-tensioning as it is normal with these C-shaped piers. And I say fortunately because adding post-tensioning would have been an extra element that our client would have to maintain and inspect. On the north end, we ended up having a conventional end bend, also founded on 24-inch square pre-stressed piles. Now, because we use weathering steel, we had to provide details everywhere, not only on the box girder, but also on the substructure, to channel the iron oxide that weathering steel sees after it corrodes. And we try to make sure that iron oxide was being taken away from the surfaces of the substructure and prevent them from staining. Now, moving on to the constructability and almost wrapping up my quick presentation here. On the MOT side, we were able to shift traffic to the existing medium since nothing was there. And the contractor had a very wide area, a playground for them to build as much as of the bridge as possible before they shifted traffic back to the final position. On the direction side, we detailed and strategically made all the top girders a maximum length of 140 feet long and maintained them to be less than 160,000 pounds. And the reason for that is that as soon as you go beyond those numbers, you start having to ask the state for permission to transport these top girders. Now, just closing this project, as you can see, some of the effects of this complex geometry, how they're driving our analysis, driving our designs, and particularly on this new infrastructure that are becoming more and more challenging and are forcing us to innovate. And all of this aggravates in a design and build environment. Thank you everyone for sticking around.
Thank you, Leo. I'd like to thank our speakers for maintaining their time slots, very efficient. We are now going to start a question and answer session. I would like to ask the presenters to come and sit here, and we can see if there are any questions. If there are questions, there are people here who have mics, so you can speak in it.
Thank you very much. Ian Firth. I just had a question for the last speaker, a challenging piece of work. I'm just very fascinated by one little detail. You painted the inside of the weathering steel boxes. Why?
So the boxes are still going to be inspected regularly. And the FDOT, so when you have weathering steel, the weathering steel, what it does, it creates a patina to protect the steel. So regular steel that is not weathering steel corrodes, that patina falls off. On weathering steel, it stays there and protects the steel, right? So that is a very abrasive surface. So the DOT requires all the inside of the boxes to be painted for future maintenance and inspectability.
Sorry, if I may just come back on that. So you lose the majority of the benefit of using weathering steel, because the purpose of using it is you avoid having to do any repainting.
Yeah, but you don't have painting on the outside. You have it on the you have it on the inside. You have it on the inside, but
well, yeah, right. You have it on the inside, and it's a base coat.
And when you inspect the inside of box girders, it's usually pretty dark, and the light color helps point
Yeah.
out any flaws in the system. So it's very beneficial.
Right.
Any more questions? All right, seeing none, would like to thank the speakers. As you can see from the projects, not all projects are just structurally driven. It's driven by other, elements that structural engineers will have unique solutions for, and these projects really demonstrate that. So thank you very much, and we'll see you next year in St. Louis.
Yep. Thank you.